But if you ask, say, A plus, I doubt it. Okay. So this will be on what are all the things which we discussed so far. Okay. And whoever is not crediting also can do it, but submit them, because I'll give you 1 week time. But within that 1 week, try to submit it so that how far you are standing, you will know essentially how much you are. I'll also have an idea where we are standing. So I'm I was actually going completely off tangent, meaning I talked about electroweak precision test for almost 6 lectures or something, 5 or 6 lectures, and it was supposed to be over in 2 lectures, and then decoupling theorem I didn't mention it. What happens at two loop I didn't mention it, and then what did I started doing the hierarchy problem actually, completely jumped and everything. But anyway, let's continue with something. We started doing the hierarchy problem, so we'll come back to the question. So module 3 and 4 are sort of interchanged in the thing. Okay, so I already said Higgs sensitivity, naturalness, Susskind, Cowell, Craig, Giudice. Okay, so I am already in module 4, whereas I didn't do module 3. Okay, module 3 I didn't I'll come back to it a little bit later. Okay, I mentioned briefly decoupling theorem. I think I just mentioned decoupling theorem, saying that if you have heavy particles in the loop, it should decouple. Essentially, it's called Appelquist-Carazana decoupling theorem. Today, I'll try to finish hierarchy of forces, and then I'll give module 3 mostly for homework or something. Let's see. Okay, let me see. I'll do. Okay, I'll jump to effective field theories a little bit. Okay, let's see how far we go. Okay, now so last week what we have been last week only, no? Yes, yeah. Horrible actually. So these are good. Okay. So last week what I tried to tell you or convince you is that if there is a scale, the Higgs mass radiative corrections are always sensitive to the highest scale in the theory. Okay, they're always sensitive to the highest scale in the theory. That's what I told you to. Now that it can be a physical scale or it can be like Pauli Wheeler's heavy fermions or whatever it is. You know Pauli Wheeler's regularization where you put in heavy fermions in the theory. Okay, so in okay Higgs mass if one assumes a higher scale and use as in Wilsonian is always sensitive to the highest scale. In the presence of a higher scale. Now, if you say that there is no Planck scale, there is no problem. Okay, if you say that there is no Planck scale, there is no problem. If you say there is no other new physics scale, there is no problem. This entire Wilson approach will work. Okay, the problem stems from the fact no symmetry to protect the Higgs mass. Okay, there is no symmetry which protects the Higgs mass. But the loop, the loop. Okay, how it's changing? Okay, this I did last week, but anyway, I'll just repeat it again. It doesn't. It is good to repeat also. It's good for me. It's good for you. Everybody essentially. So let's take in the standard model. Let's write down. What is it? Left. Okay. Kinetic. Now let's look at the diagrams which contribute to the Higgs corrections. Okay, so Higgs masses will have corrections, self corrections. Okay, this will be proportional to I lambda, and this loop, if you learn, will be Q. You take say P. So this will be some K goes to K, essentially. This coupling is I lambda, so this will be I lambda. Then there is gauge bosons sitting here. This diagram is there. Okay, this will be whatever weak, some coupling depending upon d power 4k has the same form. Okay, mz square, mw square. There will be some variation, whether there will be a cos theta w, sin theta w. So cw or sw or whatever it is. Now see this loop. This is quadratically divergent because 4 on the top and 2 on the top. Okay, so 4 minus 2, just simple power counting tells you that this is quadratically divergent. In addition, then there is also top loop. This will also be something similar. The momenta will change, but this will also be something similar. Okay, it's not completely correct because it's a fermionic thing, and you can have this is top left and this is top right. Okay, you can have P minus K. So P you can take it something else. Okay, so this is what it looks like essentially. So all of them are quadratically divergent, all these diagrams. So if you do a cutoff regularization, so the cutoff regularization tells you that is proportional to some coupling constant, say minus 1 by 16 pi square. Since minus 1 by 16 pi square just comes from the, if you make this into, because how do you show that it is quadratically divergent? You go into polar coordinates and essentially spherical polar coordinates, and then you end up having, so the radial parts you can take it out and everything essentially, and you'll end up having roughly 1 by 16 pi squares essentially, minus 1 by 16 pi square, and the only thing which will be left is the radial part. The angular part you can use. The radial part is quadratically divergent essentially. Okay, so that radial part you put it as a physical part. So this is quadratically sensitive and this holds. So suppose if you do a Wilson energy, suppose you take standard model as an effective field theory and say I want to derive it from Planck scale, because there is a scale which is sitting at the Planck, there is some new theory which is sitting at M Planck, okay, and I derive an effective field theory of the standard model, integrating all the modes above the Planck scale. I integrate all the modes above the Planck scale. Okay, standard model is sitting here. I want to derive a theory, effective theory, assuming that there is a new physics here, because I believe that there is some quantum gravity or something. There is a new scale. I can do that. I can use Wilson energy and do it. Okay, in Wilson energy, you do normally what you do if there is so integral L effective is equal to pi e power I is, say for example. Now you divide all the momentum modes, you cut them off at M Planck. Okay, you are not sending them all the way to infinity, you cut them off at M Planck. Okay, and then you integrate out the M Planck modes, all the M Planck modes, and remaining you will see. Like I explained in the last class, the fermions are protected by chiral symmetries, which is roughly the flavor symmetries. The gauge bosons are protected by gauge symmetries, masses of the gauge bosons. So what is not protected is the Higgs boson mass. Higgs boson mass has corrections which are independent of the Higgs boson mass. So if you set Higgs boson mass to 0, there is no new symmetry in the theory. If there is a fermion mass, if I set it to 0, there is a new symmetry in the theory, which is the chiral symmetries or flavor symmetries. If I set the gauge boson masses to 0, there is a new symmetry in the theory, which is the gauge symmetry. If I set the Higgs boson mass to 0, there is no symmetry as such. Complete, yeah. That's the Susskind statement, yeah.
So is it scalar that, like, to all like, is it possible to construct a symmetric for a scalar that protects it? Is it for all?
No, there are various ways of getting them essentially. So we'll consider those solutions. It's not impossible. It's not impossible. Like for example, if we at that time there were no graded Lie algebras. Okay, there was some theorem called Coleman-Mandula theorem, which tells that you cannot have internal symmetries which are of fermionic type. All possible internal symmetries are classified. So, but they didn't consider for these symmetries which are called fermionic generators. Okay, so that was later shown by Haag, Lopusonsky, and others essentially. So supersymmetry is an example where the Higgs mass is exactly protected by a symmetry at the quantum level at all orders. So you no longer have quadratic divergences. But having quadratic divergences, okay. Now the point is that suppose if this cutoff is not suppose if this cutoff, the expectation, what is the expectation? The expectation is that because the Higgs mass is around 125 GeV, there should be a new physics around 1 TeV. This is the expectation, because the correction should be around that. Okay, the correction is around that. Now, where is this entire philosophy coming in? It's coming from history. Okay, okay. Now, one thing is these quadratic divergences. Okay, I'll come to that point essentially. So this at this scale, if there is no new physics, this will go as m Planck square. So you have this issue that the Higgs mass correction is quadratically sensitive to the highest scale in the field. Now the expectation is that Higgs is not alone. There will be new physics because of various reasons, dark matter, neutrino masses, and so on. So, and this correction will be tamed so that at the scale which is the new physics scale, okay, which will be say 1 TeV or so, okay, you will get new physics. Why I chose 1 TeV? 1 TeV is the scale when the fine tuning is roughly of the order of 10 power minus 4. I said if I want to cancel this, okay, if I put Planck mass here, then I have to add a counter term roughly of the same order. I have to add a counter term roughly of the same order. Okay, so then the cancellation between this and this is 10 power minus 38. We have not seen such a fine-tuned cancellation in nature anywhere. Now you can ask where is it? The highest fine-tuning we have seen in physical systems typically is argued that the sun-earth distance. The sun-earth distance. The sun-earth distance has to be fine-tuned at 10 power minus 4. Okay, what units you take essentially at the order of 10 power minus 4 kilometers or whatever essentially. In those units, such that there is life and sun earth all this there, all the meaning there is stability of angular momentum is matches with the gravitational forces. Okay, so that is the maximum precision we have seen, but this precision is how many orders of magnitude? Over 30 orders of magnitude larger. Now you can, that looks weird, right? 10 power minus 4, it's supposed to be weird. Okay, it looks very meaning it's true that okay, most of the astrophysical things, if you see, they are look very weird. Why the sun, the solar system is so stable essentially. Okay, meaning it looks like somebody has placed the planets and everything, just like our Higgs. Okay, just like our I don't know how many of you gone to ISKCON temple. Yeah, you have gone. I think I don't remember which ISKCON temple I saw. There is one ISKCON temple in which there is an exhibition, in which explicitly they show that there is Krishna with strings, okay, and humans are attached to the strings essentially, and he's playing it. Essentially, I remember this exhibition very well. So he's fine tuning all our actions essentially. Okay, okay. So I hope this is recorded and it's on YouTube. I don't want ISKCON people on me, but anyway. But I'm saying that suppose if you don't put, say there is a pinch of salt in that, okay, if there is a pinch of salt in that, essentially that there is somebody who is organizing everything, but it somehow naturally happens that, dynamically it happens that Earth falls into the orbit such a way that in similar sense. But are there examples in particle physics in which there is a cutoff like this, quadratically divergent cutoff, and there is a new physics which came up? Okay, at that scale, there are examples. History is full of such examples. Now, it doesn't guarantee that the next example will be the same. Okay, so this history, this paper, which is extremely nice paper, I'll put it up on the and also Seth Coran's this is by Nathaniel Craig. some of the examples are present in Judice's earlier review on naturalness. This is on naturalness snow mass white paper. Here he doesn't cite Murayama, but I'll bring out that Murayama paper also. But he cites a lot of other people. Does he cite Murayama? Yes, he cites Murayama also. Yeah, number 4. Okay, I remember this. There are a lot of other papers actually. Then other one I know, which is Judice, Luti. All these are things are there. Meaning all these reviews are there, but this is sufficient to get the picture essentially because he does the full historical review. He does the full historical review essentially. So the examples we have in particle physics in which there are corrections and the main guy who did all this calculation is by Vyskov. So Murayama also cites him. So Vyskov. And I also mentioned last time that theory of large numbers, right? I mentioned the paper of Dirac, which many serious physicists also think one should not take it seriously, but okay, because they thought that Dirac in his last days didn't really do great jobs or something, should not take that paper very seriously. But independent of that, essentially, this is cited well in naturalness arguments, essentially. Okay. Independent of that, but I'll give you the physical picture where this naturalness argument work. It doesn't guarantee that it should always work. Okay, doesn't guarantee it should always work. So one of the examples is pi plus minus pi 0. Now pi 0 is a neutral. It doesn't have electromagnetic contribution. Pi plus minus charge scalar has self energy. It has self energy. So the mass difference between pi plus minus and pi 0 delta, normally there is a mass difference between pi plus minus and pi 0 because of the electromagnetic this thing, right? This you already studied in Nirmal's course essentially. Okay, now in addition to that, the one loop contribution to the mass difference between pi plus minus and pi 0, okay, this mass difference is around 15 MeV, 20 MeV if I remember correctly essentially. So this one loop contribution was calculated by Vyskov, (1939). So m plus minus square minus m pi 0 square this is not surprising that if you take a charge scalar and calculate one loop self energy, it's quadratically divergent. Okay, if you take scalar QED, compute self energy, even in ordinary QED also essentially, it's quadratically divergent. So if you express it in terms of mass difference, this comes out to be this. You are taking it as an elementary particle here. It's an elementary part for all practical purposes. Just a charge scalar, scalar QED. Different picture is that you don't you do renormalization, that is called renormalization. You put a cutoff, and at that cutoff you should either get new physics, okay, and the new physics, the old physics should not be sensitive, okay, because it should not be sensitive to the higher cutoff scale. Essentially, it should not be sensitive to the cutoff. At every scale cutoff, below that there is new completely old physics. At the cutoff there is be new physics, completely new variables, new physics essentially. And this is the scale, cutoff scale, and now you can interpret it as a physical cutoff. You can interpret it as a physical cutoff where the new physics takes over, because at this scale there is a new particle which comes, which is rho meson. The rho meson comes around this scale, okay, this gives you this. So you would expect that. Yeah, new particles should come. So this is the expectation. I am trying to tell you that where the naturalness arguments holds. This is the scale. So if you know the left hand side very well, so you can say what is the right hand side. So you can actually use Weinberg sum rules and everything and get this. Instead of this one, you can write explicitly what is the right hand sector essentially, and then check that this works, and it actually works. That you expect that the from that there is a, if there is a quadratic sensitivity to the cutoff, at that scale there is actually a new particle which comes. But this is not a fundamental principle. At most, this is an altruistic argument, essentially, some hopeful, pragmatic approach. Mm. Mm. We are taking it as a physical momentum cutoff. We are taking it as a momentum. No, in principle, you can renormalize this entire thing, right? Scalar QED is a renormalizable theory. You don't have to have this cutoff or anything. You do dimensional regression, and you can forget about the cutoff and everything. Okay, do a normal renormalization, and you get the correction and everything. At that time, you won't see the sensitivity to the high scale. Okay, when you are doing renormalization, unless you put in, if you want to see explicitly the sensitivity to the high cutoff scale, you have to put in another particle with a heavier mass into the theory, then do the dimensional regularization, and then you see that this mass difference will be proportional to the heavier mass scale. Like I said, the cowl example essentially. Last week I said the cowl. Yeah, right. So you can actually calculate with the rho meson and the A meson, okay, and do the dimensional regularization, and you see that this mass difference is actually proportional to the rho meson mass. Mm. Right? Right. It will have, yeah, right. It's we don't know, meaning in the sense that there is a tower of all these mesons actually. Yes, right. You have all this tower of mesons essentially. You have meaning until perturbating after a point that there are no mesons, right? Essentially, meaning you have mesons with vector mesons, scalar mesons. Scalar mesons we know up to whatever we have measured heaviest mesons, but after a while their lifetime is so small that they don't make a difference. Yes, you are saying something. Pardon, I didn't get the point. What scale? By gut scale. Higgs is not protected by any symmetry. So even if you forcefully set Higgs to be sitting at 125 GeV, okay, and the triplet Higgs sitting at gut scale, M gut scale, one loop corrections will make this Higgs sensitive to the gut scale, okay, and because their masses are M gut scale, the Higgs mass will be driven to gut scale. This is all dimensional regularization, no cutoff, nothing here. So this calculation was done, I think Glimner and Weinberg, 1979, 81. There are series of papers. 83, Boras company have done this calculation, shown that even if you use, yeah, Boras, the same Boras. Okay, I don't know if you are smiling for that or for some other reason. Huh? Okay, okay, right. They showed that the one loop correction in standard model inside a gut theory will push it to sensitive to the gut masses. Okay, so the gut scale masses. So the Higgs mass will be proportional to the gut scale masses. It could be fermions or scalars, whatever, sitting at the gut scale. Now here there is no Wilsonian approach, there is no naturalness arguments, there is no cutoff, but just putting the theory in a gut theory and using dimensional regularization, you showed that the Higgs mass is sensitive because it doesn't have any symmetry, sensitive to the highest mass in the theory. It could be a fermion, it could be a scalar, whatever it is. The same argument without a gut picture was shown by Cowell. If we have a heavy fermion in the standard model, the Higgs mass picks up the mass. Correction is proportional to the mass of the heavy fermion. So mass of the heavy fermion. So now that means that if you want to either put it in a grand unified theory or in a string theory or any other theory, the standard model, okay, without a symmetry protected in the Higgs mass, you will end up having a problem. You will end up having. So there is no naturalness argument here. I didn't argue any naturalness. I didn't argue about cutoff. I didn't give you Wilsonian picture. Okay, but there will always be a problem. The moment you have a specify your UV theory, either at the gut scale or a Planck scale, you will end up having a problem essentially. If there is an extra mass particle or anything beyond the standard model, the Higgs will be sensitive to it. Okay, it could be in string theory, it could be in that thing, okay, in grand unified theory or something. Now you can say that I don't care about string theory, I don't care about grand unified theory. Okay, my standard model is the end of everything essentially. Of course, nobody can do. Okay, nobody will stop you that essentially. Okay, so if you look into this picture, you don't care about quadratic sensitivity, the naturalness arguments, nothing. Okay, what you are looking at is that there is no symmetry. It's based on symmetry arguments essentially. This is based on symmetry arguments. Okay. Yeah. So then I think I covered most of the module 4, hierarchy of forces and everything. So I'll stop here and we'll consider Thursday. I'll try to show some slides on Thursday. I don't want to completely remove what is the status of the Higgs what do you call Higgs running effects in the standard model. I'll mention that, and then we'll move to effective feasibility study. Yeah. So I'll stop here today. Yeah. Any questions? I won't repeat naturalness and okay hierarchy problem again. Actually, okay. Yeah.